Hi, this is Peter with CalcBook, and today we're going to be doing a vertical brace connection utilizing the uniform force method. And we've done a video on this previously, but we've just recently completely overhauled our connection here. We've added a lot more user options for configuration and bolted connections and stuff like that. So doing another video to demonstrate all of these new features that we've recently added. So just a quick recap on our brace connection, right? This is typically part of the lateral force resisting system. We use the uniform force method to determine the forces on each of the components or at each of the interfaces. A big reference that we use to help develop this module, and we highly recommend you all referencing, is the AISC Design Guide 29 for vertical brace connections. And then we use the AISC spec for calculating all of the capacity. So for bolt shear and weld and buckling and all that sort of stuff, we go back to the spec for that information. So let's walk through all the different design checks for our vertical brace connection, because there are quite a few. So the first one is the brace-to-gusset connection. So we'll look at tensile, yielding, and rupture of the brace itself. Well, then we'll check block shear of the connection, so the block shear of the brace and block shear in the gusset. And then we look at gusset buckling for in compression. And then we look at, obviously, the bolt shear connection between the brace and the gusset, and then the bolt hole bearing and tear out and all of that. And then we get to the column-to-gusset connection, right? And this is where we have sort of a shear tab plate connection. And so we look at the tab plate weld, so the weld between the tab and the column, our bolt shear, and this would be an eccentrically loaded bolt group, our bolt hole bearing and tear out, our tab plate yielding, shear and tension, and then our tab plate rupture for shear and tension. And then we utilize interaction equations to determine the critical stresses for both yielding and rupture. And then for the beam to column connection, it's very similar to the gusset to column connection, right? We have another shear tab, so we do a tab plate weld check, our bolt shear, bearing and tear out, and then the yielding, rupture, and interaction equations. And then lastly is the beam to gusset, which is just a weld. So let's look at our problem statement for today. Right, we have the following connection configuration. We have our angle of the brace of 46.4 degrees. That's from the vertical, which is how the uniform force method is calculated. We have a W12 by 65 column with half the depth of 6.05 inches, a W16 by 57 beam with half the depth of 8.2 inches, 3/8 thick gusset plate, A36 steel. Our tab plates, we're going to utilize 3/4 inch bolts, A through 25N, not, the shear threads not excluded from the shear plane. Standard holes, 3-inch spacing typical, and 1/4 inch fillet welds. The brace is a WT6 by 22.5, and then we have some material properties there that we pulled out of the book. We're assuming 8 bolts, so 2 rows of 4 bolts, 5.5 inches between bolt rows, and then 3-inch spacing between bolts. Our loading is plus or minus 75 kips, right? So that's earthquake loading on the brace. And then we are also going to include a beam vertical load, so a reaction from our floor loading of 5 kips dead load and 10 kips live load. And one more thing before we jump into CalcBook, there's a couple things we need to calculate before we get there, and I just wanted to highlight that. The first thing is our shear lag factor. This is for the connection between the WT and the gusset plate. So our shear lag factor is 1 minus x bar over L, where x bar is the distance from the connected surface to the centroid of the shape. So you can look this up in the manual, and the distance for that is 1.13. And then our distance of the connection, or our length of the connection, is 9 inches. So when we put all that together, we have a shear lag factor of 0.874. And then we also need to calculate this vertical offset distance for our column tab plate. Typically centered on the gusset plate, but just in case you wanted to have something different, we do offer this input for relocating that tab plate. But for us, it's going to be 5.5 inches, and that will locate it centered on the gusset plate. So let's go ahead and open up CalcBook, and we'll get started on the design. All right, we got CalcBook open now. So we go and click into our 15th or 16th edition to access the vertical brace connection. We'll go into our component design, and then you'll see we've rearranged this menu a little bit, just a little bit easier to navigate. You can look at some different options here, and you can also search for designs. So just a little bit easier way to navigate through things. So let's go ahead and click on our bolted gusset, and click continue and get that loaded up. So when you enter into the gusset connection, the first thing you want to do is define your general configuration. So you can change your brace connection type from bolted to welded, right? And that will update the image accordingly and update the calculations. And then you can also update the column connection from either your shear tab or a welded connection, directly welded with the gusset to the column. But for us, we're going to be bolted and we're going to be using the shear tab, so we'll have a bolted condition. The force direction, right, this allows you to either have the applied load be checked in tension and compression, or if you want to do a single direction, you can just apply a tension force by entering a positive number or a compressive force by entering a negative number. So we'll just keep this on both directions for right now. So now we want to start entering in some of our geometric properties for the connections. So we have these laid out a little bit, but it's going to be based on our angle and our brace dimensions. So let's start first with our angle. So our angle is 46.4 degrees. Our column half depth, right, we said is 6.05. And you'll notice that as you start to enter this information, you'll get warnings if things are not correct. So for instance, now the brace is off of the gusset, right? It's no longer on the gusset here on the chamfered edge. So it'll give us warnings as things don't look quite right. Half depth of the beam is 8.2. Our brace width is 8.05 inches. So we'll go ahead and enter that in. Let's just double check that's right. And that is 8.05 inches. Okay, so now we have part of our connection laid out. The last thing we want to do before we start changing the gusset dimensions is we want to update our bolts, and then we can come back and update our gusset dimensions. So the first thing we want to do is our brace-to-gusset connection. So we'll go ahead and expand this menu here. A lot of options here, but let's go ahead and enter in our brace or our bolt diameter of 3/4, and we got to increase our bolt hole size to 1/16 over. We want to change this, right? We're going to have 4 bolts per row there. And then our center to center is 3 inches. That's correct. That's along the length of the brace. And then our center to center in the transverse direction is going to be 5.5 inches. And that'll separate the bolts out a little bit more. And then I believe the rest of everything is correct. 1.5 inch edge distances. Our brace thickness is going to be 0.575, right? That's for the flange because that's what's connected to the gusset. That's what we care about. Our gross area of the brace is going to be 6.56 inches squared. We said we had A325 bolts, so I believe this is correct for A325, not excluded, so we'll leave that there as 54 KSI. Our brace yield strength is going to be 50, and our FU is going to be 65. Our shear lag factor, right, we already calculated this, so this is going to be 0.874. And I believe that is everything for this connection. So we're going to close this menu. Go to the next menu here for our beam to gusset. No real changes here. This is just going to be a 1/4 inch fillet well. We'll leave that as is. Our column to gusset, or our column tab plate in this case, right, we are also going to have 3/4 inch bolts. Increase the size to 1/16 over. 4 bolts, 3 inch spacing. The only thing we need to adjust here is our EV, which we calculated previously at 5.5 inches. And we are going to shrink in our eccentricity from the face of the column to 2 inches. That brings us to a 1.5 inch edge distance to the gusset plate. And then I believe that is all we need to change for this. And then we can go ahead and open up our beam to column tab plate connection. Again, 3/4 inch bolts. Increase the bolt hole size. 4 bolts. And then I believe everything else, except for the A here, we'll make that 2 inches as well to make it 1.5 inch edge distance. I believe that everything else can stay as is. Okay, so now we can go back and adjust our gusset plate geometry to avoid these warnings and give ourselves a sort of a more proper layout. So we've already run some numbers in the background here to get where we think we need to be approximately. And I think we're going to be here at 24 inch of a horizontal leg, and we're going to bump this up to, I think 20 inches gets us pretty close. And then we can adjust the vertical height here, this ly2, to just basically kind of shrink the offset distance, E1 and E2 you'll see here, and get that to where we want it to be. So that's a little bit too close, right? That's less than 1 inch, so we'll go with 11 inches here on the vertical. And that gets us our general configuration for this gusset design. So we can go ahead and start working on the rest of it here. Let's go ahead and enter in our demand. So we have an earthquake load, we said, of 75 kips. And then we have a beam shear demand, the vertical load. We said 5 kips of dead and 10 kips of live. And I believe that is all we need for our inputs. If there's something else we need to adjust, we can come back and take a look at it. But I think that gets us off on the right path here. So one other thing you can look at here before we jump into the calculations, you can toggle this forces. So this will give you all of the forces at the interfaces based on the uniform force method. So it's taking the brace force and the angle and then running through all the calculations to get. But this is just a quick visual to show you what the forces are at each of the interfaces, and you can toggle that on and off. All right, so let's start jumping into some of the calculations. So the first thing is our uniform force method. Right, we've gone in detail about this before, and there's lots of good literature online about how this process works. But basically, we need to calculate some geometric properties. So the distance from the beam to the centroid of the bolted group, which is 10 inches, right? Because we placed that tab plate at the center of the 20-inch tall gusset plate. And then we want to basically assume that beta equals beta bar. This forces any eccentricities into the connection at the beam interface, which is a little bit easier to deal with when it's just a welded connection. So we set that beta to equal beta bar. And then from that, we can calculate our alpha, right, of 13.06 inches. And then our alpha bar, which is the connection divided by 2 of 12 inches. So we do get a bit of an eccentricity there, which we'll take care of with a moment on the weld. And the last thing we do is get our distance from that working point, from the gusset connection centroid to that working point of 26.39 inches. Okay, so now we can step into calculating the forces at the beam gusset interface. Right, so this is VB and HB, so we get 23 kips at V sub B and 37 kips at H sub B. And then we do have that moment to deal with, right? The difference between alpha and alpha bar is about an inch, so it's not a big moment, but we have 24.75 kip inch of force. Of moment, excuse me. And then from that, we're going to go ahead and calculate our shear per unit length for our weld design. So this will be our weld demand that we'll use using the Blodgett method. So we run through our typical sort of unit length calculations here to get our maximum shear per unit length of 0.99 kips per inch along that beam to gusset interface. So we go ahead and close this menu. And then we'll get to the column gusset connection. So we have a few different things we need to calculate here. The first is just going to be the demand due to the uniform force method. So we get our V sub C and our H sub C. And then we do the same thing. We get our unit shear for those two forces for our weld design of the tab plate to the column. And then we need to calculate the eccentrically loaded bolt group forces at the column tab plate. This is very similar to our shear tab calculation, so we're not going to go too deep into this, but we're calculating the eccentricity, we calculate our polar moment of inertia for that bolt group, and then we get the critical force on the critical bolt of 9.1 kips at the outside row. And the last thing we want to just summarize here is our internal demands on the tab plate. We'll utilize these forces for our interaction equations. So we have a moment of 56.84 kip inch, a vertical shear of 28 kips, and a horizontal or tension force or normal force of 17.19 kips. The last thing we want to do is look at our beam to column connection. The only thing that's different about this one is that we need to add in our vertical force that we inputted for the floor load. So we have our V sub B from the uniform force method, but then we also have our beam demand, right, of 16 kips. So we just add those two together, and we get a total vertical force of 39.3 kips. And then we can go through and calculate our unit weld shear like we did for the other tab plate. We also calculate our eccentrically loaded bolt group forces, and then we also do the internal demands for our interaction equations. So that summarizes the demands on this system. So we can go ahead and close these menus, and we can go and jump into the capacity calculations. And there's quite a few here, and some of them repeat, so we might skip over some of them, but we'll get the gist of what's going on here. So first, we look at our brace-to-gusset connection. So we have all the failure modes that we talked about before, right? Our brace, tensile yielding, tensile rupture, block shear of the brace, block shear of the gusset, gusset plate buckling, bolt shear, and bearing capacity of the bolt holes. So a lot of these are pretty standard, and we've done these in other calculations, right? This is just standard member design with the tensile strength. Our rupture strength is similar, right? We calculate our net section by taking out the bolt holes, applying our 0.87 shear lag factor that we calculated previously, and we get our rupture strength. Then we can calculate the block shear of the brace, block shear strength. So our block shear failure for this type is going to be a double edge failure, right? Because we have the stem of the WT down the middle, the double edge failure is going to be the critical failure for block shear. So we run through, we calculate our net shear, our net tension, and we run that through our equation from the spec to get our block shear. And then we do a similar calculation, right, for the block shear of the gusset plate. Again, taking out the diameter of the hole, and again, calculating our center failure this time for the block shear, which is going to be the critical failure mode for the gusset. We run through those same equations. And then lastly, right, we need to calculate our, or not lastly, but the next thing is our gusset plate buckling. So this is for compression of the buckling of the gusset plate. So we calculate our Whitmore width, right, which is calculated based on the geometry of the bolts and the 30 degrees. And we've done that before, but we calculate our Whitmore width of the gusset plate. We get the gross area of that section, and then we calculate our effective buckling length, right, which is just going to be the average of these three numbers. So at the center line and then at each edge of that Whitmore width, we calculate those three values, and then we determine our effective buckling length from that. From there, we do sort of a typical K/R for our slenderness, and then we go through our chapter E for compression and figure out what our critical buckling stress is and calculate the buckling strength based on that. The last two, bolt shear capacity and bearing capacity, we've touched on those before, so we're not going to get into that right now. We have lots of modules about that and different videos as well. So next, let's go ahead and jump into the beam to gusset, right? This one should be pretty quick. This is just a weld design. So we're just calculating the unit weld strength for our 1/4 inch fillet on both sides, and there's plenty of capacity there for the demand. Lastly, or not lastly, next we have our column-to-gusset connection. And the column-to-gusset and the beam-to-column are very similar. They're both tab plate designs. So we'll run this one in detail, and then we'll kind of jump into the beam-column and go over that one briefly. So first we have our column tab plate to column weld, right? And we calculated the unit shear before, so this one's pretty straightforward. We're just calculating our unit shear capacity. Then we do our bolt shear capacity, right? And this is just the bolt capacity of one single bolt, because the eccentrically loaded bolt group calculation determines the force on an individual bolt. So we calculate the individual capacity, and that's what we use for our demand capacity ratio. Bearing capacity of bolt holes, we've talked about that one before. Block shear strength, we've talked about that one before. Pretty straightforward for a shear tab. The only ones that I want to highlight here is that we do have tensile and shear forces on this tab plate. So we calculate the tensile yielding of the tab plate. We also calculate the tensile yielding of the gusset plate, and then we do the same thing for the rupture. And then we use an interaction equation to determine the combined stresses on the tab plate. So this is in the Design Guide 29 from AISC. They run through how to calculate all your nominal capacities, and then your design capacity is this interaction equation from the Design Guide. So I highly recommend taking a look at that for a deeper understanding of what they're doing here. But we use this interaction equation to understand what the combined stresses are on the tab plate. And then we do a similar interaction equation for the rupture calculations. And the last capacity is our beam to column, which we talked about is very similar. And so we have the same failure modes basically as the column tab plate. And the only thing different here is that we are including that vertical load from the beam in combination with the forces we get from the uniform force method. So same failure modes for this connection as well, so we're not going to go through that in detail. And so the last thing I want to showcase here is that we have all of this information up here up top in our summary table. So you have all of the failure modes for each of the different interfaces, and you can filter those down, right? So if you want to just look at the brace-to-gusset connection, you have your tensile yielding, rupture, block shear, buckling, bolt shear, and your demand and capacities for each of those. Or you can look at your column-to-gusset connection. So you have your gusset weld, right, your bolt shear, bolt hole bearing, block shear, so on, and your yielding and rupture interaction equations. So we've gone through a lot of work to make sure this is very easy to understand and quick access to this information, but then you can also dive really deep into the equations if that's what you want to do. So we hope you enjoyed this video of our completely overhauled vertical brace connection design module. If you have suggestions for other videos or questions on this one, please let us know in the comments below, and we'll see you next time.